Okay, let's continue in chapter 19, part 2, heat capacities of an ideal gas. We found before the previous chapter, chapter 19, that heat is equals to numbers of moles, right? Molar heat capacity times change in temperature. This is the case when volume is constant, right? We can say also like that. Heat added at a system at constant volume is equals to numbers of moles times molar heat capacity times the change in temperature. What happens if the temperature changes very infinitesimally? Okay, let's see what happens. Well, we just change this equation to this form equals to n, let's say Cv dt. Okay, but pay attention on this part. It says at constant volume. Now let's use the Phys thermodynamics. Remember, this chapter is on the Phys thermodynamics. And how do we define the Phys thermodynamics? We found that heat was equals to change in the internal energy, correct, plus work done. The same thing as before. Well, or before that, just equals to changing internal energy. Well, we're dealing with this change, right? Big changes, for example, internal energy plus P dV, delta V, correct? Delta V. Now, if we're going to infinitesimal changes, right, represent this in this way. Change in heat equals to that derivative of internal energy, right, or infinitesimal change in internal energy plus P dV, correct? But what happens if we are in this case at constant volume? Well, at constant volume, right, this quantity becomes zero, correct? Because it's constant. The derivative of a constant is zero. Perfect. Over here, the change of a quantity is constant, it's gonna be zero. Then what do we have? That heat, correct, is equal just to the internal energy. But before we found that at constant volume, right, heat is just equals to what? N molar heat capacity times dt. From here we can find that the same thing happens to the internal energy, correct? This changing internal energy is gonna be NCV dt. Correct. This equation is very important, very important in thermodynamics. But actually, this is one of the definitions for internal energy, change of internal energy, because it doesn't depend on volume and pressure. It depends only on change in temperature. So we can use this one for any case. We can use it for constant volume or when the volume is changing. Got it? Perfect. Now, we found also that for a monatomic ideal gas, right, this molar heat capacity, right, is equals to, or more specific heat is equals to 3/2, right, R. We substitute this value right here. We can find that this is equals to 3/2 N R, right, dt. Correct? This is for monatomic ideal gas. Also for diatomic, it goes to 5/2 R, and so on. Perfect. Now let's involve the case when we have heat added to a system that the volume is changing. Okay, perfect. Let's do it. So let's represent the same equation as for a constant volume. So heat at constant pressure should be equals to N molar heat capacity at constant pressure times change in temperature. Correct? Okay, great. Now let's see. Also, we can represent this in this way, right? Equals to NCP, right, dt. Correct? The same form as before. Perfect. Now, what happens when we add add this to the first law of thermodynamics. Let's do it. So what do we have? The same thing, correct? We have heat area at constant pressure is equals to changing internal energy plus P. Let's use decimal changes right here, right? PdV. Correct? But in this case, the pressure or the volume is not constant, right? It's changing. The pressure is constant, of course, according to this statement. Now let's continue then. We found that, well, when we substitute this value right here, what do we have? And right, more heat capacity at constant pressure, right? dt is equals to du. We found, right, is equals to this quantity, and right, cv dt, correct, plus now pressure is constant. Let's see what happens in this case. Look, we have that using the ideal gas law, right? PV is equals to nRT. Let's take the derivative of these two parts, and what do we have? Gonna be the derivative of PV will be equals to the derivative of nRT, correct? What should be this one? This was gonna be P dV plus V dP, correct, equals to nR dt. But this is the case when pressure is constant. If pressure is constant, we have that term is equals to 0. And we found that this, right, is equals to that, correct? So this becomes then equals to nR dt, correct? Perfect. Then let's divide it by n dt, right? N dt is cancelled, and what do we have? Cp is equals to Cv, correct? This is okay, Cv only plus R, correct? Great. Now then we have that we can solve for, we can leave it like that, right? Or solve for R, correct? R is equals to Cp minus Cv, for instance, but that's the most important one, right? This relationship, I need a new marker. Okay, a new marker, correct? It's gonna be Cp equals to what? Cv plus R. Perfect. We have one relationship between these two heat capacities, and we define gamma equals to Cp over Cv. Cp over Cv. Okay, that's a definition. Write this ratio, Cp over Cv. We use this one because it's used later in the next analysis. Perfect. Got it? Great. Now let's go to the case when we have a system, right, in a process that is called the adiabatic process. This adiabatic process heat is 0. Okay, let's see what happens when we use the first law of thermodynamics. Great. So let's go to the adiabatic process. Right. We mentioned before that we have mainly 4 processes, right? We have the process when volume is constant. We call this the isochoric process, right? When pressure is constant, isobaric. When temperature is constant, isothermal. Now when heat, right, added is 0, it has special names, adiabatic process. Now let's work with this adiabatic process. Okay, means the heat, right, the quantity is 0. Let's use this. We have this present in the first law of thermodynamics, correct? The first law of thermodynamics says again, this heat is equals to changing internal energy plus P dV. Correct? If this is 0, what happens? Well, we found that we can use PdV or we can use work, right? the idea right here is to find the work done in a adiabatic process, correct? But well, we can also use this notation like this. And what do we have? We have that this du is equals to negative p right dv. Correct? Now let's see what happens when we substitute these values that we have before. We have what? We have that this is n, the changing the energy, right, equals to n molar capacity of constant volume, right? dt is equals to negative p right dv. Correct? But again, let's use the first the ideal gas law, which says that pv is equals to nRT. Right, let's solve for p right here, and what do we have? Actually, we can send this term to this side, and we have n cv right dt plus p right dv is equals to 0. Now let's substitute this value. Let's solve for p and plug it right here, and what do we have? N cv right dt plus p, which is nRT over what? Over v right dv is equals to 0. Correct? We divide by n numbers of moles, we don't need it, and this formula is cancelled, and then we arrange this in this way. We have dt over t is equals to r over cv, correct? Molar heat capacity, volume, constant volume, times dv over volume. Actually it's plus, right? It's plus right here, is plus, right? Is equals to 0. Now let's integrate these terms, correct? And what do we have? This is ln of the temperature plus r over cv, right? Ln volume equals to a constant, correct? Equals to a constant. Let me do it right here. Okay, equals to a constant. Now let's work with this factor. We have r over cv is equals to well, when we are going back to this equation, right? To this equation, we found that r is equals to cp, right, minus cv, and this stays the same, correct? So it's equals to cp over cv, right, minus 1. But we define already this quantity, correct, as gamma. So this is equals to gamma minus 1. Now let's go back to the first equation right here, and then what do we have? Well, we have that ln, right, temperature plus ln, right, v to the gamma minus 1 is equals to a constant, correct? Perfect. So we can say that, do I missing anything right here? No, correct, I'm not missing nothing. No, not nothing. Okay, now let's see, let's combine these two. What do we have? ln of t of v gamma minus 1, correct, is equals to a constant. Perfect. And then let's cancel this ln, and what do we have? We have that t of temperature times volume gamma minus 1 is equals to a constant. Correct? So in general, when it's a constant, we can use k, right? K. We covered this when we're dealing with the ideal gas laws, right? That in this case we can represent this in this way: T1 V1 gamma minus 1 is equals to T2 V2 gamma minus 1. Correct? And this is the case for adiabatic processes. Perfect. Also, we can use pressure, correct, using the ideal gas law from here. Correct. Let's do it. So let's solve for temperature. Temperature is equals to PV, correct, PV over NR. Okay, one more time. PV over NR times V gamma minus 1, correct? That's must be equals to a constant. Perfect. Now let's do it. So it's gonna be from here this nr. Let's multiply for nr both cases. So this becomes still another constant. So what do we have? P v gamma equals to a constant. Correct. And we can represent this in this way. It's a constant. So it's gonna be p1 to the gamma is equals to p2 to the gamma power, right? And this is again the relationships volume temperature, right, and pressure volume for adiabatic processes. But the most important part right here in analysis is work, right? When we're dealing with, again, the physics of thermodynamics, one of the most important parts is work. How much work is done by the system or on the system. Okay, let's go then to finding the work done in a adiabatic process. Perfect. Let's do it. Let's do it. So we found, correct, that for adiabatic process, the change in heat is 0. Now let's go to the first law of thermodynamics, which says, right, heat is equals to changing internal energy plus, right, plus work, correct? Changing work. Perfect. Now we're looking for work in this case. Okay, work is equals to negative, correct? This changing internal energy. But how do we define again changing internal energy? Okay, we can use this equation, and what do we have? So this is equals to N, right? Cv dt is negative, correct? Now for monatomic ideal gas, we found that this quantity is equals to 3/2 R. So we can say then this equals to negative N, right? 3/2 R times dt is gonna be, right, work, the work done, right? Or we can use work in this way, correct? Equals to the change right here. Well, just use, right, t1 minus t2. Okay, we can use it, correct? In this way, so we could take this one, or we can go again to negative 3/2 nr, correct? 3/2 nr t2 minus t1. Right. This is one way how we could represent the work, right? Because this is gonna be again the same thing like this, correct? Or we can use, right, using the same in the odds, we can go to this final result, right? This is the work done. One way, we have another one, right? Of in a adiabatic process. Okay, in that way. Perfect. Now let's see what happened when we involve pressure, right? Or we substitute the temperature, correct, right here. Let's do it. Let's do it. So what do we have? We found from here, correct, or from here. We can use also from here using CV, correct. Okay, let's do it. So what do we have? Let's go to this way. Work is equals to negative N, correct, CV, change in temperature. So it's equals to N CV. Okay, CV, what else? Let's say T1 minus T2, correct? Perfect. Now, in this case, we can use pressure, right, and volume, correct? Because I want to use these quantities right here. Okay, let's do it. So what do we have then? Remember from the ideal gas law, right, which is this one. Let's solve for temperature. So what do we have? It's equals to N, right, more heat capacity, constant volume, times T1. T1 is gonna be what? Gonna be P1 V1, correct, over NR, correct. Okay, minus P2 V2 over NR. Right? Perfect. So this equals to N is cancelled, gonna be CV over R times P1 V1 minus P2 V2. Okay, perfect. Now we found before, right, in the analysis that R over CV, we found it before, right? R over CV was equals to gamma minus 1. Remember that part? We found it before. Okay, perfect. Now we apply this condition right here, and what do we have then? Okay, then we have that the work also could be represented in this way. P1 V1 minus P2 V2 divided by gamma minus 1. Correct? This is another way how we represent the work done in a adiabatic process, correct? When we have pressures and volumes, or when we have change in temperature. Okay, great. So let's make a summary of this chapter. This is the last topic for this chapter. We found, right, that when we have a system, right, at state 1, right, state, right, 1, how we specify this state? Well, it's specified now, right, by pressure, right, volume, temperature, correct, and change in internal energy, right, or the internal energy right here. Correct. Now to change from this state to another state, we have to do work or use heat. Correct. Usually, or we can have expansion or compression using adiabatic process too, right? Okay, so we have from here to here, right, using heat or using work to go to state 2. Now, how do we specify now this state? Using pressure. This is case 1, 1, 1, correct, case 1. Now right here we have case 2, V2, right, T2. Now right here we have changing internal energy, right? Give us again the condition for that state, correct? And we apply, for example, work. Work depends on what? On the process, correct? We have a constant pressure. We found already, right? We have a constant volume. A constant volume is gonna be 0, correct? Perfect. And also, if we have a adiabatic process, we found it already. Correct. We have what is that work? I raised them, right? But work was equals to negative n CV, right, delta T. This is one way. The other way was I raised it, but it was what? P1 V1 minus P2 V2, correct? 1 over gamma minus 1. Okay, and for constant temperature, we found it too, right? Constant temperature work is equals to, using the adiabat, correct? Equals to NR, right? T times ln V2 over V1. Remember that formula? Okay, so we have already all the types of work that are required when we are going from one state to another state in thermodynamics. Right? Perfect. and so on. And then we have again to another state, what we have to use what heat or work, depends on the process, to get to state 2. And we have new pressure, new volume. Also we need to involve the numbers of moles, right? Numbers of moles is involved too, right, as the state variables for the system, correct? So now, using all of these formulas, we can solve for changing internal energy, correct? We can find the state, right, according to the change in internal energy, also the new state, right, using, right, work or heat. It depends, again, heat depends if this is, the change depends if this is a constant pressure or a constant volume, correct? Well, with this analysis, we finish this chapter, chapter 19, and we are ready to start, right, chapter 20, okay, which is the last chapter for thermodynamics, and then we go to new topics. Okay, see you in the next chapter. Bye.